Hi, and we're going to be going over the basics of derivatives and calculus. So to start us off, let's just talk about what derivatives are going to help us to do. And really, we can think of these as being slope functions. So in math, you either are or have already learned the average rate of change. It's the first unit in pre-calculus. It's one of the first things you start to do in calculus AB as well. And so here's an example of constant slope. This is like algebra 1 stuff, right? From this like straight line graphs, we pick any 2 points on a line, and we can go ahead and calculate the rise over run of this line, which gives us the slope. And you can see here that my rise was 40 and my run was 10 for the 2 points I chose in the line. And if I get the slope, then it'd be 40 over 10, which is going to give me a constant value of 4. If we have curving graphs, then we can do the average rate of change. Even though it's not a constant slope, we can pick what the steepness would be on average between 2 points like P and Q here. And when we do the rise over run, the rise from point P to Q is 50, the run is 10, and we can get the average slope between points P and Q to be 5. Instead of giving graphs like this, we can also be given a linear function. So this would be, for example, the y equals mx plus b slope-intercept format of a linear equation. This is also just algebra, ninth grade physics. We did this a lot. And so we can identify what the slope is from this just by looking at the function. And in this case, we can see that our slope is going to be equal to 5. If we're given a symbolic function like this one, where this is v as a function of time, velocity as a function of time that we did in ninth grade physics, then we can identify that the letter that represents the slope would be the letter A in this, and that stands for acceleration, if you recall. We can also look at the instantaneous rate of change, and this can contrast to the average rate of change is going to be when the 2 points together, in P and Q like we were using, are so close they're essentially the same point. And so we can look at that in Desmos here to see how that would work. And when we shrink down then the distance between points P and Q, you can see that it gets closer and closer to what we refer to as a tangent line, which would be a line that touches it only at one point. And we can see here that as we look at the slope of this tangent line, I'll get this even closer together here, then it gets steeper and steeper, obviously, as we get further along the x-axis and the curve gets steeper and steeper. So what we're going to try and do then is with a nonlinear situation, a nonlinear function, nonlinear graph like we have here, we're going to try and then describe the slope not as a constant because it's not constant, right? I mean, we have to then describe it then as a function. So we're going to see how the function, the slope changes as a function of x. Now this will require us to do calculus if we just take this function like, for example, down here, y equals 5x squared plus 2x plus 6. So if we wanted to figure out the slope function, meaning what is the slope as a function of x, we're going to need calculus. And when we take the derivative, that's what you're going to be finding is a function that shows how the slope changes as a function of x since it's not constant. So we're going to just get an intro to this by looking at a graph of what we're trying to do here. So this is that same graph, and in this program we can actually change then where we're looking at on the graph, and in particular the steepness of this. So we're going to look at a couple different points that we have. So we were looking at 4, and we can see the slope is 2 when x equals 4. We're going to look at also 8, so let's go to x equals 8. The slope is now 4. When x equals 12, the slope is 6. And when x equals 16, the slope is 8. Okay. Now if we try to draw that in on this, we were looking at where it was 4. I'll try and draw a tangent line here as best I can. When it was 8, when it was 12, and when it was 16. And we said that the slope here was 2, 4, 6, and 8. Now, if we go ahead and plot those on there, we should notice, obviously, this is going to be pretty linear, right? So when we plot this, it would make sense that the slope is changing, but at a linear rate. So if we were to get a function for the line we're about to plot, it should be a linear function. And you can see here, after plotting these points at 4, 8, 12, and 16, we do in fact get a linear plot. And we could do a regression of this and realize that we could get a slope function here, which we would do by doing the long way, right? We had to get a graph, a computer to give us those slopes at different points, the slope of tangent lines, and then we had to plot them. So there's got to be a faster way to do this, because this is pretty brutal to have to do this. So obviously doing a derivative is going to be that quicker way to do it. So let's get right to it right now. So when we want to determine slope functions, which is taking a derivative, we want to just make sure we are understanding that you can, it's really called differentiating a function, but we can oftentimes just refer to it as like taking a derivative. And what that's doing is it's deriving or determining a slope function. So the slope as a function of whatever's on your x-axis. The most basic way to do this, like a rule, is referred to as a power rule for derivatives. There's many different ways we can take derivatives depending on what kind of function we're given. So if we stick to polynomials for now, which is the case for a lot of physics, especially in the first couple of units, then we can do power rule in most situations, right? So just keeping in mind, if you are in Calculus AB, you're actually going to be doing this in the middle of September. This is begins in Unit 2.5 in AP Calculus, and even sooner than that in Calc BC. So we're going to get right to it. Your math class is going to go into this in much more depth, and they're going to show you the proofs for this and everything. But right now we're using it for its utility. We need to get a slope function to do physics. So we're going to go ahead and just apply the power rule for derivatives. Derivatives in general are going to be getting a slope function. The power rule is how we do a derivative for polynomials. So if we just make up some polynomial, let's say it's y equals capital A, some constant, times x to the n power, then we can just get the slope function by taking whatever that power is, multiplying it by the function, and then we're going to reduce that power by 1. So for example, let's take a look at this example down here. When we apply the power rule to this, we are going to have the slope equal to 2 times 5x, and then we're going to subtract 1 from the power, so that's going to leave us with x to the first power. We're going to do that for this 2x term, so we have x to the 1 power is going to be then 1 times 2x, and we have to subtract a power, so that's going to make it to the 0 power. X to the 0 is 1, and we have to think of 6 then as being multiplied by x to the 0 power. Since there is no x there, we could treat it as x to the 0 power, which is 1. And when we bring that 0 out in front, then it goes away. So written in a more simplified way would be, this would be 10x plus 2. We can also do it symbolically, right, with this expression over here. So if we were trying to figure out the slope of this, and by the way, the slope actually would be the velocity, then we would be getting the derivative with respect to time, x with respect to time. So then we'd have to look at then t as being to the 1 power, right? So then you would be bringing power out in front times v naught t to the 0 power, which is simply 1. That would leave us then with simply v naught. When we do our next term, which is 1/2 at squared, we're going to bring that 2 out in front, 2 times 1/2 at, and then we have to reduce that power by 1. So t to the first power is 1. 2 and 1/2 would multiply out, and this is going to leave us then with a t. And of course, we know the equation v is equal to at plus v naught. If we remember from freshman year, we did that quite a bit. And this is actually going to be how we came about with that equation. We actually can figure out that equation using calculus. One thing of note here, so we have slope function. We're writing slope over here and slope over here. So what is the notation that we can use for doing a slope function? Now, if we remember that delta y over delta x is going to be then what we used for algebraic calculation of slope, then what we can look at here then is instead of delta y over delta x, we're going to use the letter d as a calculus notation to say that those delta x is going to be tiny and the dy, the delta y, is going to be tiny. It's kind of like when we took p and q and shrunk them together. So this is going to be the calculus version of slope. What I mean by that is algebraic slope is going to be the average rate of change, whereas dy dx is going to be considered to be instantaneous. So this is the instantaneous slope of a tangent line, whereas algebraically when we're calculating this, this would be the average rate of change. So we could have replaced this with saying dy dx equals this, and we could have replaced this with saying dy dx equals the slope function. All right, I'm going to have you guys practice this, give this a go, and see how you're doing. Thanks.